Good evening, everyone. We are going to start on neural networks today. Uh, so, so we have been through the basic machine learning. Today we are going to start with neural networks and continuing up to deep networks. Uh, Before the questions that we are going to discuss, let's discuss the basic theory behind and so. So the neural networks are inspired from the human human network of neurons that have. So as you can see the structure, okay. So messages flow through these networks, and that is how our body functions. And so the thing is that if there is a threshold, if the signal surpasses the threshold, then signal is transmitted from the network. Otherwise, not. Okay. So something like that. And so similarly our network also means this artificial neural networks also function. So the first is this signal S1 to S5, as you can see, in this weights W1 to W5. So this sum of combinations of these weighted sum is transferred to this uh, nonlinearity, okay, and this gives you the output. So this is the nonlinearity here, okay. Usually we use sigmoid function because it it shows such a feature, okay. At anything greater than 0, it gives around close to 1. Less than 0, it gives close to 0. So in fixed networks the weights are fixed, so they are uh, so that there we can infer from those networks. Adaptive networks, the weights of the network can change, okay. And the basic knowledge here, okay. So there are learning methods here, okay. So important here, so the supervised learning, as you can see that we have some output data as well, y values, okay. And so these are compared with the at every step with what the network produces. So one of these error function is least mean square, okay. so so that is used, okay. And so there is unsupervised learning methods as well. uh, so there is no external supervision, no external teacher, as you said. uh, so it self organizes the data and produces inference, okay. Supervised learning is performed offline or at a once, while unsupervised learning is performed online, one after another. So there are two types that we are going to discuss here: competitive learning and coherent neural networks. So this is our sigmoid function. So this is our sigmoid function here, and this is the graph of the sigmoid function. So first we are going off this with this x values. So x1 is 1.4, x2 is minus 2.5, and the bias is minus 0.06. the corresponding three different weights are w1, w2, w3, and this is our function fx. It is passing through the combination pass through this fx function, that is sigmoid, and it produce the output. So as you can see, so this is our combination that we get. It passes through sigmoid to produce 1 or 0. Okay. Now we are in this situation where the data set is presented as such. Okay, and the supervised values are 0 or 1. Okay, either of those, and different fields or features are there, 1.4, 2.7, 1.9 as such. Okay, and so first we initialize with random weights, and then we back propagate the loss function to calculate the new weights. Okay, next so as you can see, the decision boundary changes to fit the data, training data, and so if fx is non-linear network with one hidden layer, can in theory perfectly learn any classification problem. Okay, a set of weights exists that can produce the targets from the input. Okay, so we need to separate these two classes, as you can see, and if this is our decision boundary with two variables x1 and x2. Okay, so first we use the step activation function, so +1 or -1. So what construction we have done is this x, we have taken w2 is not equals to 0, and transform the function, transform the expression like this. Okay, so as you can see, first this is the one. Okay, our bias term. Okay, and x1 x2 are two classes, and these are the corresponding weights. Y can be plus or minus 1. Okay, if this is positive, okay, the weighted sum is positive, then the response will be positive as well, otherwise the response will be negative. Okay, this is the construction of the problem. So next we introduce the sigmoid non-linearity function. Okay, so and we have transformed a new threshold as t. Okay, so like that we're doing. Okay, and what is being shown here is this, like our expected values for x equals to 2 is 0, but what we are getting is 1. Okay, so to train the model, what we are doing is we are shifting it towards the right side to get a 0 at 2, x equals to 2. Next we have this weighted sum, and so as you can see the same construction is written again. So first we are going with the AND classifier, okay, and logic function. So as you can see, for 0 0 it gives 0, and all the rest cases also 0 except 1 1 1 1, it gives the value 1. Okay, so this is how it look like if plotted, and if x1 and x2 are 1, okay, now w1 and w2 are 1 here, okay, and w0 is minus 1.5, okay, so then this is satisfied, as you can see, and so this is it, okay, and this is our and the network, okay. For OR also this is the classifier, so minus 0.5 will come here. So ANN with hidden layers here. So the two layers can classify into two classes. So only linearly separable data can be classified with two layers. However, having three layers, that is one hidden layer, can classify into two region, a more complicated classification. So that is the one. So we have to classify into two regions, where one class is convex and another class is complement of the first class. Okay, the convex set, as you can know, that can be represented as the intersection of finite number of hyperplanes. The nodes in layer 1 can determine whether a particular sample lies in each of the hyperplane corresponding to the so this is a XOR function now. Okay, so we have to classify this one, not possible with a linear one. Okay, so we have to have non-linear classifier. Okay, it is a combination of a OR classifier and a AND classifier. Okay, and of these two. Okay, so that is the representation we have drawn here. So the 2 here minus 0.5 and another is 1.5. Okay, now nearest neighbor classifier is the next thing we are going to look at. So this is our so these are d-dimensional x vector input features vector, and we have C classes of classification. Y has C dimensions. Okay, so first what we're going to do is that there are going to be C centroids that we're going to find. Okay, Okay, so how we are going to find that? um, okay, so let's say there are C are centroids given by yi. I represents I equals to 1 to C, and this distance between x vectors and C is this one. Okay, so so summing these over, as you can see, then opening the brackets, this x is this one. Okay, the sum of squares of each dimensions, and this is the x1 and yi1. Okay, sorry, mistake here, means y is also d-dimensional here, but the centroids are C in number. Okay, so y is also d-dimensional, x is also d-dimensional, but the number of this y yi, that subscript to C, is C. Okay, so that is it. Okay, and likewise, okay, square of the y values as well. So we have to minimize this distance, okay, to get to the classifier. So what we're doing, that this is not dependent on y, means the centroid location is dependent not on this one x values. So this is the function we're going to minimize. Okay, and so for different y values we can get different g functions. Okay, and so what we're doing is that to calculate the g's, you see x is 1 to d. Okay, d dimensional. Okay, and y is similarly 1 to y I1 to YID. Okay, okay, so for x1 to xt and comparing it with y1, which is d-dimensional 1 to d. Okay, so we're getting one value, that is forming gx1. Similarly, gx2 to gxc. Okay, okay, now we're comparing. Okay, and whichever gives the highest value is our answer here. Okay, so that is going to be our new centroid location. Okay, am I audible?
Yes, yes, we can hear you.
Okay, okay, so as you see, is this comparator produces the whichever is the maximum value here from g1x to gcx. Okay, so one of these is going to be 1. Okay, means maximized and 1. Okay, so that is the idea here. And anything more to say? So let's see. Anything more? Okay, so let's continue. Okay, so this is our first one done. Okay, just going to review the things a bit and we can get started on the problems. Minutes. Okay, so we have seen the sigmoid activation function. Then we now cover a new activation function, that is the radial basis function networks. Okay, and the hidden layers which contains networks having hidden layers consisting of this activation function is called radial basis function networks. Okay, so so that is the idea. So these are the hidden layers phi 1 to phi m. Is linear activation here. Okay, and so as you can see, this is the one. X minus t this distance, L2 norm is the distance of this from t. Okay, t is some another point. Okay, so there can be different types of radial basis function norms, and these are the ones. Okay, okay, and some. So first example is this ZOR problems. Okay, so the most interesting thing is that under this radial basis function feature space, this is classifiable. Okay, means like this is linearly separable in that feature space. And to give you the example, so this is our data set. Okay, uh, suitable for ZOR. Okay, problem. So this is not linearly separable in input space, but when we apply the RBF classifier, okay, so it will be separable in that feature space. So to understand, so output space is 1 and 0, so we're constructing an RBF pattern classifier such as 0 0 1 0 0 0 1 1, so this gives 1. Okay, class 1, and this gives 0, that is class 1, and gives 1, that is class 2. Next, what we see here is that so these are the two functions that we have. So from here, as you can see, uh, for it to have two neurons at the hidden layer, so it has to have two functions as well. These are the two functions. Okay, so we've defined t1 is equals to 0 0 transpose, and t2 is equals to 1 1 transpose. Okay, okay, so what happens is that with this structure, this these points are linearly separable in the new feature space in the after we apply the hidden layer. Okay. uh, so how does this happen is what we are going to focus on now. So this is just distance, as you can see. So these are the different values that we get. Okay. Phi 1x and phi 2x is this one. Okay. Okay. For x equals to 0 0, and similarly 0 1 1 0 1 1. So we get this table. Okay. This is our new feature space in which these points are separable. Okay. Linearly separable. So this is our y function, as you can see. So this first function basis function, and second one. Okay. These two are added with a minus 1, as you can see, because they are linearly separable at this feature space. And so we are adding 1 as well. Okay. And if this is greater than 0, then it is y is greater than 0, the class is 1, otherwise it will be 0. Okay. So that is how we will linearly classify after this step. The So RBF network parameter is the center of the RBF activation function. Okay, so what the parameters that we have in the RBF is that center of the RBF activation function, the T. Okay, and the spread of the Gaussian RBF activation function. So how much it is spread, that is also important factor. Okay, the weights of the hidden layer to the output layer, the weights that are there. Okay. So learning of the weights, as you see now. So this is W1 to Wm weights are there. Okay. And so this can be transformed like this. Okay. For one example, I represent the example here. Okay. And so for n examples, you will get a matrix here. Okay. So this is the structure. D1 to Dn is the this D that we have. Okay. What actually D was here? The value it will output. Okay, 1 or 0 in this case. Okay, something like that. Yes. So we are going to minimize the squared error. Okay, and going to back propagate. Okay. So so we are taking derivative with respect to every parameter that we need to find. Okay. And so these are the ones. Okay. Wij Wij equals to, as you can see, is that let's see. I think okay. Okay. uh, J here I think represents the layer, as you can see. uh, or am I correct? No, I'm not, I think. So I is actually the layer. Okay. And J is the which neuron in that layer. Okay. So as you can see, so I is which layer we are in here. Okay. So this is 1 and 2, okay, and J represents this one or 2, okay. Okay, so that is the idea here. And so RBF has only one hidden layer, okay. Fully connected usually have more than one, okay. So in the hidden layer is linear, non-linear, and the output layer is linear. So hidden and output both are non-linear in the case of fully connected network. In fully connected hidden output neurons, they share the uh, same structure, okay. And the activation function, as you can see, the argument of so the activation function, in that we calculate the impedance distance between the input vector and the center of that unit, as you could see, the L2 norm square, okay. Argument of so this computes the inner product of input vector and the weight vector. So this is the one, right? The W transpose X. That is what it calculates. Fully connected network. Okay. Okay, it's done now. This slide is the most important one here. So we're going to train the networks here, as you can see. So the first neural network structure that we have are these types, okay. uh, don't think we're going to get into details here. uh, so this is one good important terminology: multi-layer feed for network or multi-layer perceptron, okay. So one input layer and one output layer with no hidden layers in between. This terminology is used everywhere, so important to remember this one. And so as you can see, these are the neurons, these are the layers, okay. And okay, we are going this way actually. So this is the input, this is the first layer. Should not choose back, I think. So this is the first layer, second layer, and then third layer, okay. So the one hidden layer is this one, okay. Okay, this is the one. So this is the hidden layer outputs. Okay, need to change the color here again. So this is the hidden layer outputs here. This is the final output. Okay, and to some other structure I think I cannot understand now. And this is different types of networks. Okay, so feedback network is also there, recurrent or okay. So it is something like this. Okay, so this is the out input, this is the output, but you feed back it in. Okay, and finally you take the last output sometime. Okay, something like that, but we are not going to go get into the details most probably. So hop-field network is this: every node is connected to every other node but not to itself. Okay, so every node, as you can see, one, this blue are the nodes I think. So it is connected to every other node but not to itself. Okay, and the weights are also the same. Okay, okay, so so it is similar to a recurrent neural network. Okay, in that the weight, the information can flow through it through other network. Okay, so that is the idea. So okay, so outputs of feed-forward network are fed to competitive layer. Competitive layer has the same number of inputs and outputs. Okay, which is equal to number of feed-forward networks. In the competitive layer, the output node corresponds to the maximum or in some cases minimum input fires. Okay, so it means like it works only when there is some maximum input or output, means only for that neuron it fires, when it backpropagates. Okay, not for others. Firing means here. Okay, this backpropagation happens, the weight is updated only for the minimum x or maximum x, whatever be the situation. I think this is the with respect to minimum I1, I2, I3. Okay, this is what they mean. Okay, only for that uh, weight it updates. Okay, so as you can see, D1, D2, D3 here, and these outputs are O1, O2, O3. Okay, so it can be equal to 1. Okay, or 0. Okay, so 1 only when one of these is minimum. Okay, means the D1 is minimum. So from this you can interpret whether which output is actually out of D1, D2, D3 is minimum. uh, we'll take a break. Okay, of some time, say 5 minutes, and then again we will continue. Okay. Okay, let's continue. Okay, um, so we start with Coheman neural networks. Okay, so self-organizing networks. Okay, the structure of interconnected neurons which compete for the signal. Okay, uh, self-organizing defines a mapping from input dimensional n-dimensional data space to a one or two dimensional array of nodes, okay, in a way that the topological relationship in the input space are maintained when mapped to the output array of nodes. Okay, so what it means is that uh, this x1 x2 x3 xn, you can see, so these are connected to several nodes. Okay, but somehow you can map to a two-dimensional array, this table type structure. Okay, so this is the self-organizing networks. Okay, so you have an organized way of representing data. Okay, so next we're getting to backpropagation here. uh, so with backpropagation, what you're trying to do is that you have this error function. So we'll take its derivative with respect to every parameter you want to update. Okay, and backpropagate means this one weight update rule. Okay, so this new will be old plus learning rate times this change. Okay, so that is the backpropagation for you. Okay, so that's one. Okay, next is unsupervised learning techniques in neural networks. So first we explain this competitive learning method. Okay, uh, so competitive learning method generates the weight vector. Okay, or code vector as follows. So what we are doing is that first we randomly initialize the weights. So this training vectors are applied one after another. So what does it mean is that you have x, suppose d dimensional data, so x1 to xd, and such you have n such combinations. Okay, and you apply them one two three like that online way, one after another, till you finish with n. So the output node j, okay, fires for input x. The corresponding weight is vector is updated as, okay. So if some node j, okay, fires for that input x, okay, then the weight vector is updated like this. Okay, fires means this node j produces something. Okay, means like a higher value, or that is 1 in this case. Then the weight vector is updated in this way. Okay, so the learning rate here decreases as the training progresses. Okay, okay. So the scheme is represented here. Okay, these are the y1 to y c values. Okay, and 1 to c. So whichever fires, whichever produce a 1 value, uh, that weight is updated according to this rule. And so yi depend on the weight wi. Okay, so that weight is updated. Okay, so distance between x and yi is minimized. Okay, so wi is the winner neuron. Okay, and so the winner's update rule is this. Okay, and the loser's update rule is this. Okay, so what we're doing is that we are moving the winner's weights towards the x, that is our training data. Okay, okay, so that is what we're doing, and moving the others weights away from the training data. So next is frequency sensitive competitive learning. So how many times we need to train this is determined by 1 by fi. Okay, so each time you're updating by this eta times. Okay, and so this is the update rule we have. Okay, and okay, so this is it. Okay, and so first we get this one, second f second you can see this is the one. Okay, from x1 as you can as we're using this one. Okay, so as you can see, so this is our old one x1 here. Okay, and this wi is equals to x1, this is the x2 here. Okay, x2, and wi is x1 here. Okay, so this is what we get here. Okay, 2 minus 1 is 1, 1 by 2. Okay, and next what we here, so suppose for x3 it will be 1 by 3 times this x3 plus 3 minus 1. Okay, like that we have to distribute. Okay, so 3 minus 1 is 2, 2 times this 2 will cut off, and this will remain this. Okay, so like that we have to do it. Now this is the one co-neural networks. Okay, so as you can see, it has two parameters k and t here. So for the winner, the update rule is this, means for which the the node fires, output node fires. Okay, so this is the update rule. Okay, so this distance is 0 because we're taking distance with wi and wi. Okay, so that has to be 0, but other case the distance is d. Okay, okay, and this does not work very well because the logic is explained here. So we are taking the distance minimum with this one. Okay, so first that neuron is updated, but as you can see, we need to measure the distance with x. So in that case, this distance is the least. Okay, so this is the update rule. Okay, okay, so this is the one. So now we get to the problems here. happened to this one. Some problem, I guess. Maybe I should paste with the adjoining lectures here. The paste option is not working. Okay, whatever. Uh, so so what we're going to do here is that so which of the following is not a type of neural network? So let's start with this one. So here it is. Okay, so we'll solve here. Okay, so not a tough question. So CNNR neural network, LSTM neural network, self-organizing map is a neural network type of neural network. Decision tree is not a neural network. Okay, so answer is so in this question you have to find the gradient with respect to x, y and z. Okay, so how are you going to find this one is okay, first you have to write the output here. Okay, so x and 1 is what we get to this network, so it does an inverse operation. Okay, and gives you this. Inverse operation, what does it mean by inverse operation? Okay, so focus on this question now. So this we'll do that one later. uh, so what is overfitting in the context of neural networks? The variance of the model is high. Okay, very simple one. Okay, and what is the purpose of backpropagation in neural network? To update the weights. Okay, so network's output is e to 2.5. What is the output of the sigmoid function? So you have to calculate this, you have to do this calculation. 1 plus e to the power why this is working. uh, 1 plus e to the power not working. Okay, e to the power minus 2.5. 0.924 is the answer. Okay, so a feed-forward network with one hidden layer. The input layer has 10 neurons, hidden layer has 5 neurons, output has 3 neurons. How many total weights including biases are there in the network? Sure. For these we need to know the number of input features. Achha, 10 is the one, right? Okay. Okay, so total 10 neurons are there. So if we start with a smaller example here, suppose there are 3 neurons at the start. Okay, so this is our x1, x2, x3. Okay, for each of them, but still we need to find if there are how many x. So that is difficult here. They haven't mentioned. Am I doing it right? So this is the problem. We don't know how many x values are there. Okay, so cannot be done, I guess. So there is standard 3-layer backpropagation neural network. D input units, H hidden units, C output units, and bias is there. Find the expression for output of a K output of a node K. Okay, so output of a node K, as you can see, what it would be is this is coming from the hidden layer, as you can see. So this WK0 has to be there for the bias of the final layer. Okay, WKI is the okay, so kth node, okay, and ith layer. Okay, so WKI is there, KJ, okay. And these are summed up over the how many hidden layers units are there. Okay, so the j is from equals to 1 to n. Okay, so that is there, so that is how we get the answer. So this f is again applied, okay, for the first one. Okay, so that is how we get the answer. So we have fixed learning rate of 0.01. After several epochs, you notice the loss is decreasing too slowly, indicating the learning rate is too small. If you want to change the learning rate to speed up the conversions, what value should you choose? That's too simple actually. The online vectors to be clustered are this. The maximum number of clusters to be formed is m equals to 2. Suppose learning rate geometric decrease is this. Initial weight matrix is this. The first iteration for this to cluster this will be okay. So the initial weight matrix is this one. Okay, so let's do it. We'll do this problem next time. And so this mean squared error function is there, and it's just so mean squared error will be 4. Simple. Okay, and so this is all. Okay, and thank you everyone.